Hi everybody, it's Mrs. Frame. Sorry this video is a little late. I made the whole video and once again something was wrong with my headphones and it didn't record the audio. So we're going to try this again. Hopefully it's working. I cross your fingers. Otherwise you're not getting a video and I'm going to be really mad because I put a lot of help work into it. All right, so accelerated geometry kids, you got to go all the way to the end of the video. Additional math kids, there's a set of the as a part of the last part of the video. When I tell you can turn it off, you can go ahead and turn it off. All right, so today what you're going to be taking notes on or understanding a little bit better is the altitude and hypotenuse theorems. And hang on just a moment. And what I need you to understand about what it's all about relationships. There's three relationships. It's one theorem and it has three parts and there's three relationships and they're not that hard to understand. Okay, so let's get started. Your objective is to be able to identify them when you're looking at them, know which relationship you're talking about, which relationship you need to put into practice so that you can solve the problems. So you need to be able to recognize the relationships between the parts of a right triangle and the altitude drawn to the hypotenuse. All right, so let's talk about that. First, let's talk about altitude. Altitude is a line that's is drawn from one vertex of a triangle to the opposite side, and it creates a right triangle or a right angle. Pardon me. And actually it'll create two right angles because, you know, it's perpendicular. And it's also what we call the height of a triangle. Triangles have three altitudes, three heights, but the one we're particularly learning about today is the altitude that's drawn from the right angle to the hypotenuse of the original triangle. Okay, so here's relationship number one. It's pretty basic, pretty easy to understand. I would say go grab three colored pencils or three highlighters. It's going to make things really easy to understand when you're writing your proportions and things like that. So go grab three colored pencils and then come on back. All right, relationship number one says if you draw the altitude to the hypotenuse, it creates three similar. There's a symbol for similar for those of you in additional. It's three similar triangles every single time. Okay, so basically let's go and get our colored pencils and let's look at some things. So we're going to go to the next page and we're going to do some things. Well, let me highlight a couple things actually. Let's start right here. Let's not go forward. All right, so let's talk about our original triangle. Let me put a point here at point where the altitude comes down and hits your hypotenuse. All right, here I am again. I'm sorry, I have a little tickle in my throat. Okay, so point D is this point here. Now when I drew that, I created three triangles. I had my original big one. I drew that. I got two smaller triangles. So what I'm going to do is I'm going to call my large triangle, I'm going to keep it my black triangle. My medium sized triangle is going to be my purple triangle, and my smallest triangle here is going to be my blue triangle. All right, so what I'm going to do is I'm just going to name them by their corresponding parts. So I'm going to start with my black pen, and I'm going to label the parts of my big triangle by its short leg, its long leg, and its hypotenuse. And so AB is my short leg by the way it looks. BC is my long leg, and CA is my hypotenuse. I don't know why I drew an A. Okay, so I'm going to name this triangle here from short to long to hypotenuse. So I'm going to name the black triangle, the big triangle, triangle A, B, C. It's just going up the short, cruising down the long, and then coming back up the hypotenuse. And I'm going to say that it's similar based on its relationship to the medium-sized triangle. So I'm going to go label the medium-sized triangle. Here's the short leg of the there's your right angle, there's your short leg, there's your long leg, and here's your hypotenuse of that. So let's go name that triangle now. It's triangle, and we're going to start with the short, cruise to the long, and up the hypotenuse. So this is triangle B, D, C, if you got that there. And now we're going to do the same thing with the blue triangle. And we're going to go with your short leg. So taking a look at it, this is your short leg. Here, your long leg. and here's your hypotenuse. So we're going to cruise short to long to hypotenuse. So that's A, D, B. All right. So you got to be careful when you're naming them. That is, they have to be named in the same order, by corresponding sides. So short leg, long leg, hypotenuse. Short leg, long leg, hypotenuse. From short to long to hypotenuse. That's what I did. All right. So now let's go talk about why this is actually true, because you need to know why it's true. That's even more important than knowing how to do it. Okay. So why are they similar? Okay, so if we go back and we put in our right angles, when our altitude is drawn to our hypotenuse of our big black triangle, we get a right triangle there, and a right triangle there. So we've got 3 right triangles. Okay, so what I'm noticing here is that my black triangle has a 90-degree angle. My medium triangle, or my middle-sized triangle, is got a 90-degree angle. And then my little blue, or my small triangle, has a 90-degree angle. Now, in order to prove triangles are similar, all you got to do is prove that two of their angles are congruent. Right now, each of them have a 90-degree angle, so they all have a congruent angle. All right, so now let's go and prove that the big triangle, the big black one, is similar to this medium purple sized triangle. Let me slide that down right here. And here you're going to see their right angle is here. Oh, it's supposed to be purple. And what I want to point out to you is that they actually share this angle right here. They have that angle in common. All right, so I'm going to say that this is a 30-degree angle just so that we get some measurements and we can prove some things. So if this one's 30 and this one's 30, we've got that they both have 2 measurements, 2 angles that are measuring the same size or are congruent. Okay, now let's go back and, well, let's finish that out. Now, if that's the true statement there, in our big triangle, let's figure out what our last measure has to be. Triangles add up to 180 degrees, and this is 120. So to get to 180, this has got to be 60. So we'll make this guy over here a 60-degree angle. Well, if that triangle has an angles that are 90, 30, 60, then you know what? This one has to have them as well. So that makes those similar by angle similarity. Okay, so those 2 triangles are similar. And, you know, we're going to just continue to prove it by doing the blue one, the little blue one here. Let me see if I can grab it. Here we go. I'm going to bring it down here. Now, if you'll recall, it has a right angle in it, like we said, and it also has this 60-degree angle in it, like this one, like the top one does it well as well. Okay, so that means that this top angle up here is 30 degrees. Right here, it has to be. We don't have a choice because those are the rules for triangles. They have to add up to 180 degrees. So right there, we're proving through angle similarity here that they're similar triangles based upon their congruent angles, and then through transitive property, the medium is also the same, is also similar to the little one. So they're all similar to each other, and that's always going to be the rule. Now, something you might want to learn to do when you're marking it up is that this angle, when you go to mark this angle, you can automatically come up and mark the opposite corner of the littler triangle and mark it congruent. And then you can mark this as a double mark and come up here and mark this as a double mark here, so that you can see that they're all marked up as similar triangles. So that one would be like that, and that one would be like that. See how you got that? You got your big one and then your 2 small ones. Okay, so that's why they're similar. Angle similarity, that's what you got to do. All right, let's move on to relationship number 2. Relationship number 2 says the altitude to the hypotenuse, let's add that in, to the hypotenuse. The altitude to the hypotenuse is the mean proportional to the segments it creates at the hypotenuse. All right, so if I put the altitude in here, which is, remember, it's the height between the right angle and the hypotenuse, what happens there is you get that right angle like that, or on both sides. That doesn't matter. We don't usually draw them both. what it does is it cuts your hypotenuse, which is this big guy right here, into two segments. So this is segment 1 and this is segment 2. So we're going to call this seg 1 and this seg 2. Okay, and there's our altitude. And if it's the mean proportional, what that means, if you guys recall, the mean proportional is the proportion that fits in these two spaces in a proportion, and the segs that are created go in the other two spots. So this is segment X and this is segment Y. Now, typically when you go to do this, you're not going to need to set up your proportion. You can go straight to your statement that h squared is equal to x times y, because this is always what the mean proportional does. It's 2 times 3. Remember, this is 1, 2, 3, 4. Your mean proportional is in positions 2 and 3. Their product is equal to the product of your extremes, which are 1 times 4. Okay, so remember that. It's pretty easy to use. It's just the altitude times the altitude is equal to the segment of the hypotenuse times this segment of the hypotenuse. Altitude times altitude equals little seg and big seg of the hypotenuse. Got it? That's how it goes. So let's practice one. Here's a problem for you to practice. Go ahead and label it. See if you can get it done all by yourself, and pause it and come back when you're ready. Okay, so here we go. We've got these measures. AD is 3, so I'm going to mark that as 3, and DB is 9, and it's asking us to find the measure of CD, which is our height or our altitude. Okay, so we're going to set it up. Remember, this is our right angle to the hypotenuse. This is our altitude, so it's our mean proportional. Okay, and it goes in that position, and then segment 1 and segment 2 go here. So when we cross multiply, we get h squared equals 3 times 9, or h squared equals 27, square root. H equals positive or negative 3 the square root of 3. And we have to reject the negative because why? Right, you can't have a negative measurement. And so we'll get the measurement there as 3 the square root of 3. And that's the way you're going to write the answer, unless the book asks you to give the measurement in, to the nearest tenth or something. This is the perfect answer right here. Okay, so that's practice finding using the altitude and the two segments of your hypotenuse. All right, last relationship is this one. You're going to have to read it a couple times. It seems really convoluted and hard to understand, but it isn't. Okay, so relationship number 3. Each leg of the large right triangle is the mean proportional between its adjacent segment of the hypotenuse and the entire hypotenuse. We'll come back and read that in a second. Again, let me explain it to you. Here are the legs of my right triangle. Here's my big right triangle right here. Okay, this is going to be leg 1, the short leg. This is going to be leg 2, the big leg. And right here is my hypotenuse. And if you'll recall, here is my altitude right here, drawn from my right angle to my hypotenuse, cutting it into segments. This is segment X and this is segment Y. Okay, and so basically what it says is each leg, so leg 1, A, is the mean proportional between, so that means that it's the mean proportional between the adjacent segment of the hypotenuse. So if I go and find the adjacent segment of the hypotenuse to this leg, it's talking about this segment that it's connected to. That's what adjacent means. X is adjacent to A, so that's X, over the entire hypotenuse, the whole thing, not this other segment, but the whole thing. So it would be X plus Y, the whole thing. Or we could just say, if we wanted to, C, because C is what we call in the hypotenuse if we look at it like this. Okay? One moment. Sorry about that. I was getting a phone call. All right. So basically what this means again is this is your leg that we're talking about here. So we would write A squared is equal to, and again, segment X was adjacent to leg A. So x times the entire hypotenuse, which we marked as c. And so that's the problem we're going to want to solve. So why don't you try to do the mean proportional, or the leg 2? Do the problem that's going to help you solve or set up your mean proportional for leg 2. Okay? And when you're ready, you can just come back and see if you did it right. All right, and so basically here, leg 2 is the mean proportional. So B is our leg 2, so it's going to go in this position and in this position. That's our mean proportional between the adjacent part, which the adjacent segment of the hypotenuse would be in this section. In this situation, it would be segment Y on the over the or and the entire hypotenuse, which is C. So there we have b squared equals y times c, right? So that's going to help us find some numbers that we're going to need to find here in a second. Let's practice one. So here's a practice problem. If you want to go ahead and try it on your own, go ahead and press pause and try it. If you want to watch me do it, you can watch, because there's another practice one after this. All right, so AD is 3 and DB is 9, and we're looking for AC, given our information up here. So I'm looking for the leg of my big right triangle here. And I've got these two segments here. Now I've got a leg. Is this relationship 2 or relationship 3? Relationship 2 talks about the altitude's relationship to the segments. Relationship 3 talks about the legs' relationships to the segment over and the hypotenuse. Okay, so we need to find the measure of the hypotenuse, which if we add those two is 12. So if we're trying to find x, and the leg is our mean proportional, goes in these two positions, and its adjacent segment is this segment right here, and the entire hypotenuse is this segment right here, or the whole side right there. And then you're going to multiply, cross multiply. 3 times 12, x squared equals 36. Square root them both. X equals positive or negative 6. Obviously, we're going to reject negative 6. X equals 6. And there we have a measurement. Now we could go back and, if we wanted to, find the height of this if we wanted. We could have done that doing relationship 2. But you can see your right triangle. You can start finding all your measurements if you need to. But this keeps you from doing the Pythagorean theorem, and it's pretty fast. So you should keep practicing. Here's another one. All right, go ahead. Pause and then come back when you're ready to watch. All right, so DB is 21, AC is 10, and we're looking for AD. Now this one's a little bit different. Again, you got to think about what relationship you're dealing with. Here's your right triangle here. This is your altitude to your hypotenuse. So let me put that measurement in there, that little mark in there, so we know for sure. And we've got a leg, we've got a segment, and we've got another segment of our hypotenuse. So we have a little bit more complicated problem going on here, because we don't know the length of the hypotenuse, but we do know that it's whatever x is, it's plus 21. So remember that your leg is your mean proportional, so it's 10 and 10. And then you've got your adjacent side, which is x, and then your entire hypotenuse, which is x, whatever that is, plus 21. So we're going to multiply that and get 100 equals x times x plus 21. We're going to multiply that, distribute. We get 100 equals x squared plus 21x. And you know it's got to equal 0 when you have an x squared, so that you can factor or use your quadratic. So we're going to move the 100 over here. So we get 0 equals x squared plus 21x minus 100. We'll move that out of the way. Let's factor out 100. So I'm thinking of the factors of 100 that are 21 apart, and I know I got to subtract. I'm thinking 25 and negative 4. What do you think? X and x, 25x minus 4x gives us 21x, so there we go. So when we go to write out our equation here, we're going to get x plus 25 and x minus 4 equals 0. So we'll set them both equal to 0, and that gives us x equals negative 25 or 4. And we have to reject 25 because we can't have a negative distance. This is 4. Our hypotenuse is 25. So that's another application for relationship number 3. All right, so if you're an additional, I think you are done. Yes, you can go ahead if you're in additional math and just summarize your notes and write down some good questions. If you're in accelerated, let's take a look at this proof because it's a little bit of a beast and I want to make sure you're prepared. Okay, so let's take a look at what we're given and what relationship it's going to lead us to discuss. All right, so let's take a look at what we're supposed to prove. Maybe we could work backwards. PO times PM. PO times PM. All right, well, that's interesting. Typically, that's going to come off of your altitude squared equals your segment times your segment of your right triangle, possibly. And then we want PR and PJ. Now that's going to come off of a leg squared equals a segment times the entire hypotenuse. But let's see if that's actually where we're going to go. Let's start with our givens here. We got PK is perpendicular to JM. Okay, so it's going to give us those two right triangles there. And once we have that in there, I think that that's going to give us two right triangles, and then that'll allow us to go discuss these, because if we can then talk about this one being the altitude to that, then we can say that we can use that altitude to cut this into segment and hypotenuse, and we can say that PK times PK is equal to PR times PJ. So we could do that and get that statement using these two, this first one and this one right here. Then let's go see how we'd figure out this one. We got PO and PM, and we have KO and PM are perpendicular, so that would give us this right here. And then we want to state that maybe KO is squared is PO times PM, but I really need them to have something in common here. PO times PM. Okay, so PO times PM. What am I looking at here? PO times PM. So we're looking at this one again. So it's pretty much a similar statement that PK again. So if we're using this right triangle, the altitudes, cutting segments, I think we got it here. Okay, so let's start off with our first given. We got PK perpendicular to JM. That's a given. And that's going to give us some right angles, which is in turn going to give us some right triangles. So we're going to say that angle PKJ and angle PKM are right angles because perpendicular segs form right angles. And I'm sorry for the messy handwriting. I got to tell you, this is the second time I've made this video. All right. So let's move on to number 3 and see where that takes us. Let's go take a look at, let's focus on this little triangle here. Okay, so we've got a right triangle in there, or a right angle in there. Let's go and grab this next statement right here, and let's establish that PR times PJ is PK times PK. Okay, let's use relationship 3. So let's establish that by going RK and JP, a given. And then that's the altitude to the hypotenuse. And so, and it's coming off a right angle and right triangle, so we can state that. So let's state that it's an altitude. We need to state that it's an altitude. Let's say that KR, that's okay, is an altitude. All right, and so we're going to say a segment drawn from a vertex to opposite side is altitude. Okay. Oh, vertex to drawn from vertex to of a vertex, let's say, of a triangle perpendicular to the opposite side is an altitude. So let's make sure we get that correct. All right, so that gives us that information. And now that we've set up that this is an altitude and it's the altitude to the hypotenuse, we can now go and make this statement. I want to talk about these two. So if I look at this triangle here, let me highlight it. If I look at this triangle right here, this leg of KP squared is adjacent, or KP is adjacent to PR. And so that's why I'm mentioning KP versus KJ, because I want PR times PJ. I want these two. So I need this leg, not KJ, because KJ would give me JR and JP. You understand? All right, so let's go and state that PK squared, that quantity squared. We don't have to write the mean proportional, by the way. You can if you want to add an extra step to your proof, but you don't have to. PK squared, it's the mean proportional between PR times PJ. Okay, and that's going to take care of, we've made that statement there. All right, so now we got to talk about how to shorten this reason here. So let's go back up here. If altitude to hypotenuse, then the leg is the mean proportional. You can just do NP. I know what that means. Between adjacent seg of hypotenuse and hypotenuse. Okay, that's about as short as I can make it. All right, so there it gives you that. And then I've established this part of my proof. Now if I'm done with this statement here. So now I'm going to go back and I'm going to grab this statement here. So instead of doing all of this jazz over again, all of it, I'm just going to go back and say similarly, because I'm doing exactly the same set of steps with this one here. Let me highlight it. I'll do it in purple, PK, this purple, PK squared is PO times PM, or PO times PM. Got it? So PK squared is PO. So it's the same set of steps. So we don't have to write it. We can just say similarly, PK squared is equal to PO times PM. And for a reason, you say C1 through 5. Okay? And now you see that we've got PK squared equal to these two things, and now I've mentioned that thing. And I can use transitive property here to say then PO times PM right here can replace PK is equal to PR times PJ. And that's the transitive property. And that's how you would apply relationship number 3, or I think it's theorem 68C. Okay, there you go. That's all I got. Summarize and come to class tomorrow ready to go. Bye.